Welcome everybody to exercise 5 in the first worksheet. So in this exercise, we are going to consider the function f of z 1 over z to the 4 times sinus of z. We want to show it admits a Laurent expansion on an annulus with inner radius 0 and outer radius pi and center 0. So we have here the center 0, and then the outer radius is pi, so maybe pi is somewhere here. And therefore we get an annulus of this type, which basically is just a disk with a point, with a center point removed. So as in exercise 4, we want to understand where the function f is holomorphic. So first of all, where is the function f of z equal to 1 over z4 sinus of z holomorphic? So the only thing we have to check is that the denominator is not 0, because z to the 4 is then holomorphic, sinus of z is holomorphic, so the only problem is that the denominator could be 0. So it must be z to the 4th times sinus of z different from 0. So this means z to the 4th different from 0, and sinus of z different from 0. So the first condition on z, this is the same as saying that z must be different from 0. And what do we know about the sinus of z? So we know that sinus of z vanishes exactly at the integer multiples of pi. So this one is then equivalent to z different from k pi, where k is just an integer. So we see that the problematic points are 0 here. Let me do them in red. Are 0 here. Then there is pi. There is then here 2 pi. And so on, 3 pi here. And then we have minus pi, minus 2 pi, and so on this other side. So shortly, this annulus is a set where the function f is holomorphic. So this implies that f is holomorphic on the annulus a0 pi, which center 0. And as in exercise 4, this implies that f has a Laurent expansion in the annulus a0 pi 0. So we can write f of z as the sum for n going from minus infinity to plus infinity of an z to the n. And the goal of this exercise is to find the principal part. So now we want to find the principal part of this function f, and to show that it's equal to this formula given there. So in order to do this, we have to go back to the formula for f, and I want to now expand sinus of z in power series around 0. So to do to find the principal part, we consider first power series expansion of sinus of z around z0 equal to 0. So what is this expansion? So this is given by z minus z cube divided by 6, which is 3 factorial. And then we have plus z to the 5th power divided by the factorial of 5, which is 120. And we have then other terms here. But the important thing is that now I can rewrite this as z times what? Times 1 minus z squared over 6 plus z to the 5 over 100 and, sorry, z to the 4th over 120 and so on. So basically what I have here is z times 1 minus some function, let me call this function g of z, where g of z is the function z squared over 6 minus z to the 4th over 120, and then there are some other terms here missing. Okay, so let me then substitute this expression for sinus of z inside the formula for f that we have here. Let me now use the formula for f. So f of z is 1 over z to the 4th sinus of z. And we can rewrite then sinus of z as z times 1 minus g of z. So this is 1 over z to the 5th. Yes, let me write it like this. So this is 1 over z to the 5th times 1 over 1 minus g. So what we know about this function 1 minus g? So we know that the function 1 minus g is holomorphic. 1 minus g is holomorphic. And never 0 in the disk of radius. In the disk of radius pi and center 0. So in the disk d pi 0. Why is that so? Because you know the function 1 over 1 minus g is exactly the function sinus of z divided by z, no? Because 1 minus g is just a function sinus of z over z. And we know that this function is not 0 in 0 because g is 0 in 0, so 1 minus g is equal to 1 in 0. And it's also not 0 in all the other points of the disk because the sinus function is not 0 at those other points. So this function 1 minus g is non-zero at all points in the disk. So this implies that the function 1 over 1 minus g is holomorphic. on d pi 0. So it has some power series expansion. So this means that 1 minus g is equal to some power series expansion. So this will be a0 plus a1 c plus a2 c squared plus a3 c cubed plus a4 c to the 4 plus a5 z to the 5, and you can go on forever. But let me then see what why is this power series important for us, because now we can use this power series to give a Lorentz expansion for f. So then remember f of z is 1 over z to the 5th times 1 over 1 minus g. So this means this times a0 plus a1z plus a2z squared plus a3z cubed plus a4z to the 4th. And then here you have other terms. But observe that these other terms don't matter for the computation of the principal part. Also, these higher order terms, they do not matter for computing principal part of f, because these terms here have powers z to the 5, to the 6th, and so on, and these powers then kill z to the power of 5, and so these are then in the end powers in z which are not negative. No, so we can indeed rewrite this as a0 over z to the 5 plus a1 z to the 4th plus a2 z to the 3 plus a3 z to the 2 plus a4 z and other terms. And you see these other terms, they don't contribute to the principal part. So we want to find now the principal part by finding the coefficients a0, a1, a2, and a3, and a4. And how are these coefficients given? These are the coefficients given by this relation over here. 1 over 1 minus g is this expansion. So now we want to find this expansion for 1 over 1 minus g. And to do so, we are going to use the geometric series. So let's find power series expansion of 1 over 1 minus g up to order 4. This is what we have to do now. So we use the geometric series. So we know that 1 over 1 minus g z, this is 1 plus g of z plus g squared of z, and so on. And we know that we can do this around 0. So this is converges for small norm of z, since g of z, what is g of z? G of z was written above, if I remember correctly, was z to the 2 over 6 minus z to the 4 over 120 and other terms. So this means that g of 0 is equal to 0. So this means that for small norm of z, then the norm of g is also smaller than 1. So the series converges. So what we have here, now we have to find then the power series expansion of all these terms, g of z, g squared of z, and then sum all them together. But we notice that we need to do this only up to g to the 2, because all the other terms will have order, contribute to order bigger than 4. So remember, we need only to find things of order up to 4. So, for example, for g of z, we already have the expansion written here on the right. So this is z to the 2 over 6 minus z to the 4 over 120. And then here there are other terms, which I write like this, O of z to the 5, which means these are all terms of order at least 5. So these are the terms in coming from g of z. So I can write also here g of z here on the right. I could also have written like this, O of z to the 5. And then it comes g squared z plus other terms. So now I want to compute g squared up to order 4. And you see here g squared up to order 4. What do I have to do? I have to take the square of the first term. Then I should take products of all the other terms here. But you see, already taking the square of the first term gives me here a power of 4. So all the other terms will also be of order bigger than 5. So this is just the square of the first term, square of z squared over 6. These are all the other terms are of order at least 5. Okay, so we get this new term of order 4, z to the 4 divided by 36. And now if we go on like this, g to the 3, for example, then here you get z to the 6 over 6 to the 3rd, plus terms of order at least 7, and so on. So g to the k, this is always z to the k divided by 6 to the k, plus terms of order k plus 1. So these terms here, so these terms are of order at least 5 if k, sorry, here I forgot one, this is 2k, sorry, this is 2k and this is 2k plus 1. No? So, because we started with z squared, so 2k and 2k plus 1. So these are word at least 5 if k is bigger or equal than 3. Now, so you see that all these terms here don't contribute to this sum with order less or equal than 4. So this means that we have here 1 minus z squared over 6 plus z to the 4th. And then from g squared, we get this z, sorry, this was a minus, z4 divided by 36. And then all the other terms here are of order at least 5. Okay, because we saw that they come either from terms of order at least 5 from G or terms of order at least 5 from G squared. And then for higher powers of G, these terms are all of order at least 5. So here we have found almost what we need. This is plus z squared divided by 6. And then what is the coefficient of z to the 4th power? This is 1 over 36 minus 1 over 120. And you can compute easy. This number is over 360, and here is 10 minus 3. So this is 7 over 360. Okay, so then this gives us these coefficients. This gives us these coefficients here. Now, so A0, what was A0? A0 is 1. So this means that A0 is 1. A1 is 0. A2 is 1 over 6. A3 is 0. And A4 is 7 over 360. Now, so we have found then all these coefficients that we can then go and substitute back here. So thus, f of z is 1 over z to the 5. Then we have 1 over 6z to the 3. And then plus 7 over 360 z. And then we have other terms here which come to the regular part, so plus the regular part. So this is here then the principal part. Right, so this gives us the expansion we wanted. So let's sum up what we did. So we had this function 1 over z to the 4 sinus of z. First of all, we checked that this function is holomorphic on the disk minus 1 point, the disk with center 0 and radius pi. And now what we have to do, we have to consider the power series expansion of sinus of z, which we did here. And what we did, we first got rid of one factor of z, and then the rest is 1 minus g. This function is never 0 in the disk, which means that when I take 1 over 1 minus g, this is a holomorphic function, so I can expand it in power series. And this gives me then the Laurent expansion of f up to any order I want. So I simply take 1 over z to the 5, and then multiply by this power series expansion of 1 over 1 minus g. So now the only problem is to find this Taylor series expansion for 1 over 1 minus g. And to do this, we used this trick with the geometric series. So we know that we have this expansion by the geometric series, and we also know the first terms of the power series expansion of g. So this is given here on the right. And now what I have to do is that I want only terms of order up to 4. Also, this is the important thing, only terms of order up to 4, because they are the only ones that contribute to the principal part of f. And you see that for g, I already have written here what are these terms up to order 4. No? Z to the square over 6, and then z to the 4 divided by 120. And then for all the other powers of g, I have to see what are the terms of order up to 4. So for g squared, I did this here. So I just took the expression above, and then you see you have to take the square of the first term. And then there will be other mixed terms multiplying z squared with z4 to the 120, and so on. But all these terms will have order strictly bigger than 4, so they can be ignored. And now if I go to higher powers of g, then all terms will be of order bigger than 4, because g starts already with z squared. So this means that g to the third will start with z to the sixth. In general, g to the k will start with z to the k. So all these terms will not contribute for k bigger or equal than 3. And then now I collect all my terms. So I have these 2 terms here. I have this 1 term here. And then I collect them all together here, and then just take the sum. So do some simplification, I find the coefficients that I write then here. And these coefficients give me back the principal part of f. Okay, thank you very much.